The night sky is lying to you. Look up on a clear, dark night, away from the city lights, away from the glow of civilization. You might see thousands of stars scattered across the darkness like diamonds on black velvet. You might even catch a glimpse of the Milky Way itself, that river of light stretching across the heavens. And if you're lucky, if you know where to look, you might spot a faint fuzzy patch of light in the constellation Andromeda. That fuzzy patch is the Andromeda galaxy, 2.5 million light-years away. It contains 1 trillion stars. It's hurtling through space at over 100 kilometers per second, and it looks close enough to touch, but it's not. In fact, despite appearances, despite all our technology, despite every achievement of human engineering and every dream of science fiction, the Andromeda galaxy might as well be on the other side of an infinite wall. Because here's the uncomfortable truth that nobody wants to talk about. We will never reach another galaxy. Not in your lifetime. Not in 1,000 lifetimes. Not even if humanity survives for millions of years and develops technology we can barely imagine today. The universe itself has made other galaxies unreachable, not through malice, not through accident, but through the fundamental laws of physics, through the expansion of space-time itself, through barriers so absolute that calling them impossible to overcome is actually an understatement. This isn't a story about what we haven't achieved yet. It's not about limitations we might one day surpass. This is about the hard stop at the edge of human possibility. This is about the moment when ambition meets reality and reality wins. So the question isn't whether we'll reach another galaxy someday. The question is, when did other galaxies slip forever beyond our grasp? And are we watching right now as even more of the universe becomes permanently unreachable? Welcome to the Cosmic Cage. Welcome to the truth about our place in the universe. Welcome to the story of why, no matter what we do, humanity is trapped in its own backyard for all eternity. Before we can understand why we can't reach another galaxy, we need to understand what a galaxy actually is. And more importantly, we need to understand just how mind-breakingly far away they are. Let's start local. You're on Earth. Earth orbits the Sun. The Sun is just one star among roughly 200 to 400 billion stars that make up the Milky Way galaxy. Our galaxy is a spiral galaxy, about 100,000 light-years in diameter. It's shaped like a disk with spiral arms, and our solar system sits about 26,000 light-years from the galactic center, out in one of those spiral arms called the Orion Spur. Everything you can see with the naked eye in the night sky, with a tiny handful of exceptions, is part of our galaxy. Every star, every constellation, Orion's Belt, the Big Dipper, Polaris, Sirius, all of them are neighbors, cosmically speaking, living in the same galactic neighborhood. The brightest star in our night sky, Sirius, is only about 8.6 light-years away. That's practically next door in cosmic terms. The furthest individual star visible to the naked eye is V762 Cassiopeia, roughly 16,000 light-years away, still well within our galaxy. But the Milky Way isn't alone. The nearest major galaxy to ours is Andromeda, also known as M31 or Messier 31. It's slightly larger than the Milky Way, containing around 1 trillion stars compared to our few hundred billion. Under dark skies, away from light pollution, you can see it with the naked eye as that faint smudge I mentioned earlier. It's the most distant object visible to the unaided human eye, and it's 2.5 million light-years away. Now, I just threw out light-years like it's a casual unit of measurement, but let's actually process what that means. A light-year is the distance light travels in 1 year. Light moves at approximately 299,792 kilometers per second, or about 186,200 282 miles per second. In l'instant 1 second, light covers a distance equal to travelling around Earth's equator about 7.5 times. Think about that for a moment. In the time it takes you to, say, 1 Mississippi, light could circle the entire Earth more than 7 times. In 1 minute, light travels about 18 million kilometers. In 1 hour, about 1.08 billion kilometers. And in 1 year, light travels about 9.46 trillion kilometers. That's 9,460 billion kilometers. Nearly 10 trillion kilometers for every single light year. To put this in perspective, the Moon is about 384,000 kilometers from Earth. Light from the Moon reaches us in about 1.3 seconds. The Sun is about 150 million kilometers away. Light from the Sun takes about 8 minutes and 20 seconds to reach us. When you look at the Sun, you're seeing it as it was 8 minutes ago. Neptune, the furthest planet in our solar system, orbits at about 4.5 billion kilometers from the Sun. Light from Neptune takes about 4 hours to reach Earth. The edge of our solar system, defined by the Oort cloud, extends to about 1 light-year from the Sun, and Andromeda is 2.5 million light-years away. Multiply those numbers out, and you get a distance of approximately 23.65 quintillion kilometers. That's 23,650 billion kilometers. Let me give you some context for this number. If you could drive a car at highway speed, about 100 kilometers per hour, non-stop toward Andromeda, it would take you about 27 billion years to get there. The universe itself is only 13.8 billion years old. You'd need twice the current age of the universe, driving constantly, to cover that distance. If you flew on a commercial airliner traveling at 900 kilometers per hour, it would take you about 3 billion years. If you traveled on the International Space Station, which orbits at about 28,000 kilometers per hour, it would still take you roughly 96 million years. The distance from Earth to the Moon is about 384,000 kilometers. Humanity's greatest journey, the Apollo missions, covered that distance. It took 3 days. To cover the distance to Andromeda at Apollo mission speeds would take trillions of years. The distance from Earth to Mars, which we're actively planning to reach, varies between about 55 million and 400 million kilometers, depending on where both planets are in their orbits. When Mars is at its closest, at about 55 million kilometers away, it's roughly 3 light minutes from Earth. Andromeda is 2.5 million light-years away. There is no human frame of reference for this scale. Your brain cannot truly comprehend these distances because nothing in your daily experience comes close. The largest distance you've probably traveled in your life, perhaps a flight across an ocean, might be 10,000 or 15,000 kilometers. Andromeda is more than a quadrillion times farther than that, and Andromeda is the closest major galaxy. Beyond Andromeda lies the Triangulum Galaxy, about 3 million light-years away. It's the third largest galaxy in our local group, containing about 40 billion stars. Then there's the Large Magellanic Cloud, a satellite galaxy of the Milky Way, about 160,000 light-years away. The Small Magellanic Cloud sits about 200,000 light-years away. These are dwarf galaxies, smaller than Andromeda or the Milky Way, but they're still galaxies with billions of stars. The local group, our galactic neighborhood, contains about 80 galaxies total, bound together by mutual gravitational attraction. This entire structure spans about 10 million light-years. Beyond the local group, you find galaxy clusters. The nearest major galaxy cluster to us is the Virgo cluster, about 54 million light-years away, containing approximately 1,500 galaxies. Beyond that, superclusters. Our local group is part of the Virgo supercluster, which itself is part of an even larger structure called Laniakea, spanning 520 million light-years and containing about 100,000 galaxies. And beyond that, the cosmic web, the large-scale structure of the universe, stretching across billions of light-years, containing hundreds of billions of galaxies. When we talk about reaching another galaxy, we're talking about crossing distances so large that they challenge the very concept of travel. We're talking about the Andromeda Galaxy because it's the closest major target, and if we can't reach Andromeda, we can't reach anything beyond it. Every other galaxy is even farther away, even more impossible. But even saying we can't reach Andromeda doesn't capture the true scope of the problem. Because the barriers aren't just about distance, they're about speed, about energy, about time, about the nature of the universe itself. And each of those barriers, examined carefully, reveals the same truth. This isn't merely difficult, it's impossible in ways that most people don't fully grasp. Let's start with the most obvious problem: speed. Humanity has built some fast machines, jets that break the sound barrier, traveling faster than 1,200 kilometers per hour. The SR-71 Blackbird reached speeds over 3,500 kilometers per hour. Rockets that escape Earth's gravity achieve velocities exceeding 40,000 kilometers per hour. The space shuttle re-entered the atmosphere at about 28,000 kilometers per hour. Spacecraft that journey to the outer reaches of our solar system achieve even higher speeds. The Voyager 1 probe, launched in 1977, is currently traveling at about 61,000 kilometers per hour relative to the Sun. It's the most distant human-made object, now in interstellar space, over 23 billion kilometers from Earth. And it's been traveling for more than 45 years. The New Horizons probe, which flew past Pluto in 2015, reached speeds of about 58,000 kilometers per hour. The Juno spacecraft orbiting Jupiter travels at about 265,000 kilometers per hour during its closest passes to the planet. And the fastest human-made object ever created is the Parker Solar Probe, launched by NASA in 2018. During its closest approaches to the Sun, it reaches speeds of approximately 690,000 kilometers per hour, or about 192 kilometers per second. That's monumentally fast. It's fast enough to travel from London to New York in about 30 seconds. It's fast enough to travel from New York to Tokyo in less than a minute. It's fast enough to circle the Earth in about 3.5 minutes. By the standards of anything we encounter in daily life, it's incomprehensibly rapid. And yet, it's nowhere near fast enough for intergalactic travel. Let's do the math. Andromeda is 2.5 million light-years away. That's approximately 23.65 quintillion kilometers. The Parker Solar Probe travels at 192 kilometers per second. Divide the distance by the speed, and you get the travel time. The answer? Approximately 3.9 billion years. Let me repeat that. Using the fastest spacecraft humanity has ever built, it would take 3.9 billion years to reach the Andromeda Galaxy. For context, Earth itself is only about 4.5 billion years old. The Sun formed about 4.6 billion years ago. Complex life on Earth has only existed for about 600 million years. Multicellular life emerged roughly 800 million years ago. Before that, Earth was dominated by single-celled organisms for billions of years. Dinosaurs went extinct 66 million years ago. Humans, Homo sapiens, have been around for roughly 300,000 years. Anatomically modern humans emerged maybe 200,000 years ago. Behaviorally modern humans, with language and culture, maybe 70,000 years ago. All of recorded human history spans less than 6,000 years. The entire span of human civilization, from the first cities in Mesopotamia to today, is roughly 10,000 years. We're talking about a journey that would take longer than the entire history of complex life on Earth. A journey that would span almost the entire age of Earth itself. And that's assuming the spacecraft could maintain that speed indefinitely, which it can't. The Parker Solar Probe only achieves those velocities during close passes to the Sun using gravity, assists. In deep space, far from any gravitational bodies, it would slow down considerably. Without continuous propulsion, it would coast at a much lower speed, perhaps comparable to Voyager 1, extending the journey time even further. But let's be generous. Let's imagine that we develop propulsion technology far beyond anything we have today. Let's say we build a spacecraft that can travel at 10% the speed of light. That's about 30,000 kilometers per second. It's roughly 156 times faster than the Parker Solar Probe. It would require revolutionary breakthroughs in physics and engineering. It would require energy sources that don't currently exist. But let's assume we achieve it. At 10% light speed, the journey to Andromeda would take 25 million years. Still impossibly long, still far beyond the timescale of human civilization, or even human existence as a species. Homo sapiens hasn't even existed for 500,000 years. Our entire evolutionary lineage from the last common ancestor we share with chimpanzees spans only about 6 to 7 million years. A journey to Andromeda at 10% light speed would be more than 3 times longer than humans, and chimpanzees have been separate species. It's longer than the time since our ancestors first walked upright. It's longer than the entire story of human evolution. What about faster? What if we could reach 50% the speed of light? That cuts the journey down to 5 million years. Still incomprehensibly long, still multiple times longer than humans have existed. Still longer than our hominid ancestors have walked upright. The genus Homo, which includes modern humans and our extinct relatives like Homo erectus and Homo habilis, has only existed for about 2.8 million years. At 50% light speed, the journey to Andromeda would still be almost twice as long as our entire genus has existed. Even at 90% the speed of light, approaching the absolute maximum possible speed in the universe, the journey would take nearly 2.8 million years. That's longer than the genus Homo has existed. That's longer than recorded history by a factor of more than 400. That's more generations of humans than have ever lived. And here's where it gets worse. The speed of light isn't just a speed limit like a highway speed limit, where you could, in theory, go faster if you had a powerful enough engine. The speed of light is an absolute cosmic limit built into the structure of reality itself. According to Einstein's special relativity, published in 1905, nothing with mass can reach the speed of light, let alone exceed it. This isn't a technological limitation. This is a fundamental law of physics. As you approach light speed, several things happen. Time dilation kicks in, meaning time passes more slowly for you relative to the outside universe. If you're traveling at 90% light speed, time passes about 2.3 times slower for you than for someone stationary. At 99% light speed, about 7 times slower. At 99.9% light speed, about 22 times slower. Length. Contraction occurs, meaning distances appear to shrink in your direction of travel. From your perspective on a near light speed spacecraft, the distance to Andromeda would appear shorter than 2.5 million light years. But that's only from your perspective. From the universe's perspective, the distance remains the same, and your relativistic mass increases, requiring exponentially more energy to accelerate further. This last point is crucial. As you get closer and closer to light speed, accelerating becomes harder and harder. The faster you go, the more massive you effectively become from an outside observer's perspective, and the more energy you need to accelerate further. At 90% light speed, you already need tremendous amounts of energy to go any faster. At 99% light speed, you need vastly more. At 99.9% still more. At 99.99% even more. The energy requirement approaches infinity as your speed approaches the speed of light. This isn't an engineering problem. This is physics saying, no, it's not about building a better engine. It's about the fundamental structure of space-time preventing you from reaching or exceeding light speed. And even if you could somehow reach 99.99999% the speed of light, you'd still need over 2.5 million years to reach Andromeda from the universe's perspective. The time dilation would make the journey feel shorter for the travelers, perhaps a few thousand years subjectively instead of millions. But that doesn't help with the fundamental problem. The rest of the universe, including everyone you left behind, would still experience millions of years passing. Your civilization would be long gone. Your species might be extinct. Your home planet might not exist anymore. Speed alone makes intergalactic travel impossible on any timescale relevant to human civilization. A journey that takes millions of years from the universe's perspective means you're effectively traveling to a completely different future. You'd return, if you returned at all, to find that everything you knew was gone. But speed is just the first barrier. The really nightmarish problems begin when you ask, how do you achieve even a fraction of light speed? The answer involves energy, more energy than you can possibly imagine. Let's talk about what it actually takes to move something fast. Really fast. Close to the speed of light fast. Energy is the fundamental currency of motion. Every time you accelerate an object, you're adding kinetic energy to it. In classical physics, at low speeds, the kinetic energy equals 1/2 times mass times velocity squared. But at relativistic speeds, approaching light speed, the formula changes. The energy increases exponentially, approaching infinity as you approach light speed. For space travel, this creates a problem so severe that it effectively kills the dream of intergalactic travel before it even begins. Start with the rocket equation. Formulated by Konstantin Tsiolkovsky in 1897, it's the fundamental mathematical relationship governing all rocket propulsion. In simple terms, it says that to go faster, you need more fuel. But here's the catch. That fuel has mass, so you need more fuel to carry that fuel, which means you need even more fuel to carry that fuel. It compounds exponentially. The equation is change in velocity equals exhaust velocity times the natural logarithm of initial mass divided by final mass. For low speeds, this is manageable. For getting to the Moon, or even Mars, we can work within these constraints. The Saturn V rocket that took astronauts to the Moon had a fuel-to-payload ratio of about 50:1. For every kilogram that reached the Moon, 50 kilograms of fuel were burned. That's enormous but achievable. For Mars missions, similar ratios apply. But for relativistic speeds, speeds approaching light speed, the rocket equation becomes a death sentence. Let's run some numbers. Suppose you want to accelerate a spacecraft to just 10% the speed of light using conventional chemical rockets. Chemical rockets, like those used in the Space Shuttle or Saturn V, achieve exhaust velocities of about 3 to 4 kilometers per second. That's the speed at which the exhaust leaves the rocket. Using the rocket equation with an exhaust velocity of 4 kilometers per second and a target velocity of 30,000 kilometers per second, 10% light speed, you would need a mass ratio of E to the power of 7,500, that's E, Euler's number, approximately 2.718 raised to the 7,500th power. This number is so large, it's essentially meaningless. It's incomprehensibly vast. To give you an idea, there are about 10 to the 80 power atoms in the observable universe. The number we're talking about is incomparably larger. There literally isn't enough matter in the universe to build a chemical rocket that could reach 10% light speed. That's not hyperbole. The amount of fuel required exceeds the total mass available in the entire observable universe. Chemical rockets simply cannot achieve the speeds needed for intergalactic travel, period. They can't even achieve the speeds needed for fast interstellar travel within our own galaxy. The rocket equation forbids it. Okay, so chemical rockets are out. What about more advanced propulsion? Nuclear propulsion, where you use nuclear reactions, either fission or fusion, to heat propellant and expel it at high velocity. This is better, much better. Nuclear fission rockets, which have been seriously studied since the 1950s, could achieve exhaust velocities of 10,000 to 20,000 meters per second or 10 to 20 kilometers per second. That's about 5 times better than chemical rockets. Nuclear fusion rockets, which are still mostly theoretical, could potentially achieve exhaust velocities of 100,000 meters per second or 100 kilometers per second. That's 25 times better than chemical rockets. With nuclear fusion propulsion, you might achieve exhaust velocities approaching 1% the speed of light with advanced designs. This dramatically improves the mass ratio. To reach 10% light speed with a fusion rocket, achieving 1% light speed exhaust velocity, you'd need a mass ratio of about e to the 10th power, or about 22,000 to 1. That means for every kilogram of payload, you need 22,000 kilograms of fuel. That's enormous, but at least it's a finite number. It's theoretically possible, if incredibly impractical. But remember, we're trying to reach Andromeda, 2.5 million light-years away. At 10% light speed, that's still 25 million years. We need to go faster, much faster. And as you increase the target velocity, the mass ratio explodes exponentially. To reach 50% light speed with that same fusion rocket, you'd need a mass ratio of about e to the 50th power, or about 5 times 10 to the 21st power. That's 5 sextillion to 1. For every kilogram of payload, 5 sextillion kilograms of fuel. The Earth's mass is about 6 times 10 to the 24th kilograms. You'd need a fuel mass equal to roughly 1,000th of Earth's mass for every kilogram of payload. To send a modest spacecraft weighing 10,000 kilograms, you'd need fuel equal to about 10 times Earth's mass. The numbers simply don't work. What about antimatter? When matter and antimatter collide, they annihilate each other and convert 100% of their mass into energy, according to Einstein's famous equation E equals mc squared. 1 kilogram of matter plus 1 kilogram of antimatter yields about 1.8 times 10 to the 17th joules of energy. That's about 43 megatons of TNT equivalent, or roughly the energy of the largest nuclear bomb ever detonated. This is the most efficient energy source theoretically possible under known physics. If we could harness antimatter for propulsion, we'd have the best rocket humanity could possibly build with current scientific understanding. And it's still not enough. Even with antimatter propulsion, the energy requirements for relativistic travel are staggering. The most efficient antimatter drive would be a photon rocket, where matter and antimatter annihilate, and the resulting gamma rays are directed backward as propulsion. Photons traveling at light speed provide the maximum possible exhaust velocity. With a photon rocket to accelerate to a velocity v, you need a mass ratio of the square root of the quantity 1 plus v over c divided by 1 minus v over c. For 10% light speed, that's a mass ratio of about 1.1 to 1. Not bad. For 50% light speed, about 1.7 to 1. Still manageable. For 90% light speed, about 6.3 to 1. Getting significant. For 99% light speed, about 14 to 1. That means for every kilogram of payload, you need 14 kilograms of matter-antimatter fuel, or 7 kilograms of antimatter and 7 kilograms of matter. And that's just to accelerate. To slow down at your destination, you need the same amount of fuel again. So you need to double it, and you need fuel to accelerate the fuel you're using to decelerate. The math gets complicated, but essentially you're looking at roughly 50 to 1 or higher for a round trip to high relativistic speeds. Now let's scale this up. A minimally viable interstellar spacecraft might mass 1,000 tons or 1 million kilograms. That includes the spacecraft structure, life support systems, supplies, crew, scientific equipment, everything. To accelerate that to 90% light speed and decelerate at the destination, you'd need roughly 50 times the spacecraft mass in fuel. That's 50 million kilograms of matter-antimatter fuel, or 25 million kilograms of antimatter. Here's the problem. Humanity has produced approximately 20 nanograms of antimatter in total, ever, across all particle physics experiments combined. That's 20 billionths of a gram, or 0.00000002 grams. To produce 25 million kilograms would require increasing our antimatter production by a factor of roughly 10 to the 21st, or 1 sextillion. It's not a matter of scaling up by 10 or 100 or even a million. We'd need to increase production by a sextillion. The energy expenditures required are mind-boggling. Creating 1 kilogram of antimatter requires at least 25 billion kilowatt hours of energy, assuming perfect efficiency, which is impossible. In reality, with current technology, it's closer to several trillion kilowatt hours per gram. For 25 million kilograms, even with perfect efficiency, you'd need 625 trillion kilowatt hours. Total human energy consumption in a year is about 170 trillion kilowatt hours. You'd need almost 4 million years of total human energy output, assuming perfect conversion efficiency. And current antimatter production is nowhere near perfectly efficient. Realistically, with current technology, you'd need quadrillions of years' worth of human energy output. And even if we could produce that much antimatter, we'd need to store it safely. Antimatter cannot touch normal matter, or it annihilates instantly. We currently store tiny amounts of antimatter using magnetic containment, suspending charged antiparticles in a vacuum using powerful magnetic fields. The largest amounts ever stored are measured in trillionths of a gram, and only for a few hours or days before the antimatter is lost. Storing kilograms, let alone millions of kilograms, for years or decades during a journey is beyond our current capabilities by an almost infinite margin. But let's keep being absurdly generous. Let's imagine we solve all these problems. We develop cheap antimatter production. We discover how to store vast quantities safely. We build the spacecraft. We load the fuel. We accelerate to high relativistic speeds. We've now encountered a new problem, relativistic mass. According to special relativity, as an object approaches light speed, its relativistic mass increases. The formula is relativistic mass equals rest mass divided by the square root of 1 minus v squared over c squared. At 90% light speed, an object's relativistic mass is about 2.3 times its rest mass. At 99% light speed, it's about 7 times its rest mass. At 99.9% light speed, about 22 times. At 99.99% light speed, about 70 times. This means that the faster you go, the more massive you effectively become, and the more energy you need to accelerate further. The energy requirement doesn't just increase linearly with velocity, it increases exponentially. At speeds very close to light speed, it approaches infinity. This is why nothing with mass can reach light speed. You literally run out of energy in the universe before you get there. Even if you had infinite fuel, the energy required to push that last fraction of a percent toward light speed exceeds any finite amount. The universe says no. And there's another issue. Even if you could reach these speeds, traveling at relativistic velocities through space is incredibly dangerous. Space isn't empty. It seems empty, but it's not. The interstellar medium, the space between stars, contains roughly 1 hydrogen atom per cubic centimetre. That sounds sparse, and it is by terrestrial standards. But at relativistic speeds, those atoms become lethal. A single hydrogen atom impacting your spacecraft at 90% light speed would hit with the kinetic energy of roughly 1.5 times 10 to the minus 13th joules. That's a tiny amount, but there are a lot of atoms. Flying through space at 90% light speed, you'd encounter roughly 10 to the 12th atoms per second per square metre of frontal area. That's 1 trillion atoms per second per square metre. Each one hits with high energy. The cumulative effect is a continuous bombardment of radiation and impacts that would erode, damage, and irradiate your spacecraft and everything inside it. You'd need shielding, massive amounts of shielding, heavy metals, meters thick, to absorb the impacts and radiation, which adds mass, a lot of mass, which requires more fuel to accelerate, which compounds the already impossible fuel requirements. Even with shielding, some radiation gets through. High-energy cosmic rays, particles accelerated to near light speed by supernovae and other violent cosmic events, would bombard the spacecraft continuously. Over a journey lasting thousands or millions of years, the cumulative radiation dose would be enormous, damaging electronics, degrading materials, and potentially causing lethal doses of radiation to any biological organisms aboard. Every solution creates new problems. Every technological advancement we can imagine runs into the same fundamental barriers: exponential energy requirements, relativistic physics, and the sheer scale of the distances involved. We're not talking about building a better rocket. We're talking about overcoming the fundamental laws of physics. And those laws don't negotiate. But here's the thing. Even if we solved all of this, even if we somehow found unlimited energy and built impossible machines and accelerated to near light speeds and survived the journey, there's a bigger problem lurking in the background. A problem that makes all of these other challenges seem almost quaint by comparison. The universe itself is expanding, and that expansion changes everything. In 1929, astronomer Edwin Hubble made one of the most important discoveries in human history. Studying distant galaxies using the Mount Wilson Observatory's 100-inch telescope, he observed that distant galaxies are moving away from us. More importantly, he discovered that the farther away a galaxy is, the faster it's receding. This relationship, now known as Hubble's law, led to a stunning conclusion. The universe itself is expanding, not expanding into something, which is a common misconception, just expanding. Space itself is stretching, carrying galaxies along with it like dots drawn on an inflating balloon. If you draw dots on a deflated balloon and then inflate it, the dots move apart, not because they're moving across the surface of the balloon, but because the surface itself is stretching. The universe works the same way, except in 3 dimensions instead of 2. For most people, this is where the conversation ends. The universe is expanding. Okay, cool. But the implications of this expansion are profound and devastating for any hope of intergalactic travel. Here's what expansion means in practical terms. Take 2 galaxies separated by a certain distance. As time passes, the space between them increases. They're not moving through space. The space itself is growing. The galaxies are essentially stationary in their local reference frames, but the distance between them increases anyway. It's counterintuitive, but it's how the universe works on the larger scales. The rate of this expansion is described by the Hubble constant, currently measured at approximately 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. So for every 3.26 million light-years of distance, the recession velocity increases by 70 kilometers per second. This means that a galaxy 3.26 million light-years away is receding from us at 70 kilometers per second due to cosmic expansion. A galaxy 6.52 million light-years away is receding at 140 kilometers per second. A galaxy 32.6 million light-years away is receding at 700 kilometers per second, and so on. Andromeda is about 2.5 million light-years away, roughly 0.77 megaparsecs. If the universe's expansion applied uniformly, Andromeda would be receding from us at about 54 kilometers per second. But here's a crucial detail. Andromeda isn't receding. It's actually moving toward us at about 110 kilometers per second. Why? Because the Milky Way and Andromeda are part of the same gravitationally bound local group. Gravity, on these local scales, overcomes the expansion of space. The mutual gravitational attraction between the galaxies in the local group is strong enough to pull them together despite the expansion of the universe. The local group is held together by mutual gravitational attraction, so expansion doesn't drive us apart. In fact, Andromeda and the Milky Way are on a collision course, which we'll return to later. This is fortunate for anyone interested in potentially reaching Andromeda, except we've already established that's impossible for other reasons. But it's important to understand that local gravitational binding can overcome cosmic expansion. However, this only works locally. The local group spans about 10 million light-years, and within that volume, gravity dominates. Beyond the local group, expansion dominates. And here's where things get truly disturbing. The expansion of space means that distant objects are receding from us at speeds proportional to their distance. At large enough distances, this recession velocity exceeds the speed of light. Wait, I hear you saying, I thought nothing could go faster than light? That's correct. Nothing can move through space faster than light. Objects cannot travel through space at superluminal velocities, but space itself can expand at any rate. There's no speed limit on the expansion of space itself, and when space expands fast enough, objects carried by that expansion can recede from each other at superluminal velocities faster than light without actually moving through space at all. They're stationary in their local reference frames. It's the space between them that's growing. This creates a boundary called the cosmological event horizon, sometimes called the Hubble sphere. Beyond this horizon, the recession velocity exceeds the speed of light. Objects beyond this boundary are receding from us so fast that light they emit now will never reach us. It will travel toward us, but the space between us and the light is expanding faster than the light is traveling through space. The light is running on a cosmic treadmill that's moving faster than light can run. And more relevant to our discussion, we can never reach them even if we could travel at the speed of light. Even if we instantly accelerated to light speed and traveled forever, we would never reach them. The space between us is growing faster than we can traverse it. Currently, the cosmological event horizon is at about 14.5 billion light-years away in co-moving coordinates. Any galaxy beyond that distance is receding from us faster than light speed and is forever unreachable, even in principle. There is no technology, no matter how advanced, that could reach them. The universe has placed them permanently out of reach. But it gets worse. The expansion of the universe isn't constant, it's accelerating. Observations of distant type Ia supernovae in the late 1990s by two independent research teams revealed that the expansion rate isn't constant and isn't slowing down as was previously expected. It's increasing over time. The universe is expanding faster and faster. This discovery, awarded the Nobel Prize in Physics in 2011, was shocking. Physicists expected that the mutual gravitational attraction of all the matter in the universe would slow the expansion over time, perhaps even eventually reversing it, leading to a big crunch. Instead, they found acceleration. This acceleration is attributed to dark energy, a mysterious property of empty space itself that causes it to expand faster and faster. We don't know what dark energy is. We don't understand its nature. We just know it exists because we can measure its effects, and it dominates the energy content of the universe. About 68% of the universe is dark energy. About 27% is dark matter. Only about 5% is ordinary matter, the stuff we're made of, the stuff stars and planets are made of. Dark energy is causing the expansion to accelerate, and as far as we can tell, it will continue accelerating forever. Because of this acceleration, the cosmological event horizon is actually shrinking in terms of proper distance. Galaxies that are currently within reach, that we could theoretically reach if we left now traveling at light speed, are being pushed beyond the event horizon. They're slipping away, and once they cross that threshold, they're gone forever. Right now, as you're listening to this, galaxies are slipping beyond the cosmic horizon, becoming permanently unreachable. Not in a billion years, not with advanced technology, not ever. The universe is literally removing pieces of itself from our possible future. Every second, more galaxies cross that boundary, and this affects even nearby galaxy clusters. While Andromeda itself is safe, being gravitationally bound to us, most of the galaxies we can currently see are not. They're being carried away by expansion, and many of them are already beyond the reach of light-speed travel. Here's a specific example. The Virgo cluster, a collection of about 1,500 galaxies located about 54 million light-years away, is receding from us at approximately 1,200 kilometers per second due to cosmic expansion. It's not yet beyond our cosmological event horizon, but it's moving away fast. Its recession velocity is about 0.4% the speed of light. Even if we could instantly accelerate to light speed, even if we ignored all the energy problems and engineering challenges, we would still face the expansion of space working against us. Every second we travel toward a distant galaxy, that galaxy moves farther away. We'd be running on a cosmic treadmill, and the treadmill is speeding up. For galaxies beyond the local group, space is expanding faster than we could ever travel through it. Reaching them isn't just impractical, it's physically impossible even in principle, even with infinite technology, even with perfect efficiency. The universe itself forbids it. The universe, through its expansion, has put most of itself forever out of reach. We exist in a bubble of accessibility, and that bubble is shrinking. The cosmos is becoming less connected over time, not more. The universe started from a dense, hot state 13.8 billion years ago in the Big Bang, and it's been expanding ever since. For billions of years, gravity and expansion were in competition. In the early universe, matter was dense enough that gravity could form structures, pulling matter together to form galaxies and clusters despite the expansion. But as the universe expands, the density of matter decreases. And as dark energy dominates more and more, the expansion accelerates. We're entering an era where the expansion is winning decisively. And there's nothing we can do about it. We can't stop the expansion. We can't slow it down. We can't opt out. The laws of physics are dragging galaxies away from us, and we're helpless to prevent it. This brings us to one of the most unsettling concepts in cosmology: the difference between the observable universe and the reachable universe. The observable universe is the sphere of space from which light has had time to reach us since the Big Bang, about 13.8 billion years ago. Because the universe has been expanding during that time, Objects that emitted light 13.8 billion years ago are now much farther away than 13.8 billion light years. Due to the expansion, the observable universe extends about 46.5 billion light years in all directions, encompassing everything we can possibly see, even in principle. This includes galaxies that emitted light billions of years ago, light that's been travelling toward us ever since, fighting against the expansion of space. The most distant galaxies we can observe are over 13 billion light-years away in light travel distance, meaning the light has been travelling for over 13 billion years. But due to expansion during that time, those galaxies are now more than 30 billion light-years away in co-moving distance. The observable universe contains about 2 trillion galaxies. 2 trillion, each containing billions to trillions of stars. The numbers are almost incomprehensible. The reachable universe is smaller, much smaller. It's the sphere of space we could potentially reach if we left right now traveling at the speed of light, and if our journey lasted forever. And due to the expansion of the universe, this sphere is far smaller than the observable universe. Currently, the edge of the reachable universe is about 18 billion light-years away in co-moving coordinates. That's the distance to the farthest galaxy we could theoretically reach if we left today traveling at light speed, assuming our journey lasted forever and we could maintain light speed indefinitely. Anything beyond that distance? Unreachable. Forever. We could launch a light speed probe today, and even if it traveled for trillions of years, it would never reach galaxies beyond about 18 billion light-years in current distance. The expansion would push them away faster than the probe could approach. And remember, this assumes light speed travel, which we've already established is impossible for anything with mass. The realistic reachable universe, based on achievable speeds, is far smaller still. At 10% light speed, the reachable universe would be tiny, probably only a few hundred million light-years in radius, containing only a small fraction of the local supercluster. At more realistic speeds we can currently achieve, like the Parker Solar Probe's velocity, the reachable universe is essentially just the local group. Maybe. Barely. But here's the truly depressing part. The reachable universe is shrinking. As the expansion of space accelerates, more and more galaxies cross beyond the cosmological event horizon. Galaxies that are currently within the reachable universe will, over time, be pushed beyond our reach. The sphere of space we can access is getting smaller with each passing moment. Calculations suggest that in roughly 150 billion years, give or take, every galaxy outside the local group will have been pushed beyond the cosmic horizon. Future observers in our galaxy, or in the merged Milky Way Andromeda system, won't be able to see distant galaxies at all. They'll have disappeared beyond the horizon. If we wait too long to begin our journey to a particular galaxy, that galaxy might slip beyond reach before we could arrive, even traveling at light speed. The universe has an expiration date on travel opportunities, and that date is approaching. Not on human timescales, but on cosmic timescales. For us, practically speaking, most galaxies are already unreachable. The few that are theoretically reachable will slip away over the next tens to hundreds of billions of years. In the far future, trillions of years from now, the local group will have merged into a single giant elliptical galaxy, and everything beyond it will have receded beyond the cosmic horizon. Future astronomers in that distant era won't be able to see other galaxies. They won't be able to observe galaxy clusters or superclusters. They won't be able to measure the expansion of the universe or the cosmic microwave background radiation. They might conclude that the universe is just one galaxy surrounded by endless void, eternal and unchanging. They'll be cosmologically isolated, with no way to learn the truth about the cosmos beyond their local neighborhood. They won't be able to discover the Big Bang or cosmic expansion or dark energy because the evidence will be gone, hidden beyond the event horizon. And we're headed in that direction. For us right now, the situation is better, but not by much. We can observe billions of galaxies. We can study the large-scale structure of the cosmos. We can see the cosmic web, the filaments of galaxies stretching across hundreds of millions of light years, separated by vast voids. We can study galaxy clusters and superclusters and the flow of matter on the largest scales. But we can't reach any of it. We're observers trapped behind an unbreakable window, watching a universe we'll never touch. It's like being in a museum where you can see priceless artifacts behind glass, but can never hold them, never interact with them, never truly experience them except visually. And even the parts we theoretically could reach, like Andromeda, are protected by the other barriers we've discussed: distance, time, energy. The universe has layered impossibility upon impossibility, ensuring that humanity remains confined to its local cosmic neighborhood. The cosmic horizon isn't just a distance, it's a prison wall, and unlike the horizon on Earth, which recedes as you approach it, always staying the same distance away, the cosmic horizon is absolute. Cross it, and you can never come back. Light you emit after crossing the horizon will never return to your origin. The information about what lies beyond becomes forever inaccessible to those who remain behind. This raises an uncomfortable question. If we can't reach other galaxies in space, what about time? After all, time dilation at relativistic speeds means travelers would age more slowly than the universe around them. Could we use time as a workaround for the distance problem? Could we put people to sleep for thousands or millions of years and wake them up when they arrive? Could generation ships work? The answer reveals yet another barrier to intergalactic travel: biology itself. Let's imagine for a moment that we solve all the physics problems. We build a spacecraft that can reach a significant fraction of light speed. We have unlimited energy. We somehow navigate the expanding universe. We have the fuel, the shielding, the propulsion. We're on our way to another galaxy. Now we face a new question. How do the passengers survive? Even at high relativistic speeds, even with time dilation working in the traveler's favor, intergalactic journeys would take tens of thousands to millions of years from the perspective of the universe outside the spacecraft. And while time dilation would reduce the subjective experience of time for the travelers, it doesn't eliminate it. At 90% light speed, time dilation means time passes about 2.3 times slower for the travelers. A journey that takes 2.5 million years from Earth's perspective would only take about 1.1 million years from the traveler's perspective, still impossibly long. At 99% light speed, time passes about 7 times slower. The journey would take about 357,000 years subjectively, still far too long. At 99.9% light speed, time dilation means time passes about 22 times slower for the travelers. A journey that takes 2.5 million years from Earth's perspective would only take about 114,000 years from the traveler's perspective. That's still impossibly long. Longer than modern humans have existed. Longer than any civilization has persisted. Longer than any human lifespan by 4 orders of magnitude. Longer than recorded history by a factor of almost 20. You cannot keep a person alive for 114,000 years. Even if you could slow aging indefinitely, even if you could prevent telomere shortening and cellular senescence and all the biological mechanisms of aging, the human body and mind weren't designed for such timescales. The psychological effects alone would be catastrophic. A human being living for 114,000 years would experience roughly 1,600 lifetimes worth of conscious existence, assuming a normal lifespan of 70 years. The mind would change beyond recognition. Memories from the beginning of the journey would fade and distort. Identity would shift and evolve. You wouldn't be the same person at the end who you were at the beginning. not by any reasonable definition of personal identity. So let's consider alternatives. The most commonly proposed solution is the generation ship, a massive spacecraft designed to support a self-sustaining population across multiple generations. The original travelers would have children, who would have children, who would have children, across thousands of generations, until their distant descendants finally arrived at the destination. This concept appears frequently in science fiction, and it sounds plausible at first glance. But examine it closely, and the problems multiply exponentially. First, population size. You need genetic diversity to avoid inbreeding and genetic drift. Inbreeding causes recessive genetics disorders to become expressed more frequently, leading to health problems and reduced fitness. Genetic drift, random changes in gene frequencies in small populations, can lead to loss of genetic diversity and potential fixation of harmful alleles. Studies on minimum viable populations suggest you need at least several hundred individuals to avoid these problems in the short term, and several thousand for long-term genetic health. One widely cited study suggests a minimum of 160 people for a journey lasting several generations, assuming careful genetic management. But for journeys lasting tens of thousands of years, you'd need substantially more, probably at least several thousand, maybe tens of thousands. Second, resources. This population needs food, water, air, living space, and energy for tens of thousands of years. The spacecraft would need to be massive, essentially a small world, a city in space. You'd need closed-loop life support systems that can recycle waste with near-perfect efficiency across geological timescales. Current life support systems on the International Space Station recycle about 90% of water and generate oxygen by electrolysis. That sounds good, but a 10% loss rate compounded over thousands of years is catastrophic. You'd need 99.99% efficiency or better, maintained for tens of thousands of years. Any leak, any inefficiency compounds over millennia. If you lose even 1/10,000th of your water per year, after 10,000 years you've lost more than half. You need perfect recycling, which is theoretically impossible due to entropy. Third, maintenance. Systems break, equipment fails, electronics degrade, mechanical components wear out. The spacecraft itself would need constant repairs and replacement of components. The International Space Station requires regular maintenance and periodic replacement of major systems. Components fail regularly and must be repaired or replaced. But you're traveling through interstellar space with no possibility of resupply. Every spare part, every raw material needed for repairs must be carried from the start. If you need to replace a turbine, you need spare turbines. If you need spare turbines, you need raw materials to manufacture them. You need machine shops, 3D printers, fabrication facilities. You need engineers who know how to use them. You need to train new engineers every generation. Knowledge must be preserved and transmitted across thousands of generations. The mass requirements become prohibitive, and some components simply cannot be manufactured in space with portable equipment. Computer chips, for example, require sophisticated fabrication facilities. If your computers fail after a few thousand years, can you build new ones? Fourth, psychology. Imagine being born on a spacecraft, knowing you will die on that spacecraft, knowing your children and grandchildren and great-great-great-grandchildren, hundreds of generations of descendants, will all die on the same spacecraft, never seeing the destination. What kind of social structure could maintain morale and purpose across such timescales? Human civilizations on Earth rarely persist more than a few centuries in recognizable form. Languages change over generations. English in the year 1024 is barely recognizable to modern English speakers. English in the year 1424 is challenging. Cultures evolve, values shift, Political systems collapse and reform. The Roman Republic became the Roman Empire, became fragmented kingdoms. Nations rise and fall. Religions transform. And that's with the stability and resources of planetary existence. On a generation ship, cut off from outside influences, isolated in a confined environment, populations would change dramatically over time. After a few thousand years, the language spoken would be unrecognizable to the original travelers. The culture would be completely different. The descendants might not even remember why they're traveling. Maintaining institutional memory across hundreds of generations is extraordinarily difficult. Knowledge can be lost. Purpose can be forgotten. Myths and legends replace historical records. The original mission might be reinterpreted, distorted, or abandoned entirely. Fifth, mutation and evolution. Over tens of thousands of years, genetic drift and mutation would change the population. In the isolated environment of a generation ship, with limited population size and unique selective pressures, evolution would occur. The beings that arrive at the destination might not be the same species that departed. Natural selection would favor traits suited to life on a spacecraft rather than planetary life. Individuals who adapt well to microgravity, confined spaces, and artificial environments would have more offspring. Over thousands of generations, the population could diverge significantly from terrestrial humans. They might develop different body proportions, different immune systems adapted to the spacecraft's specific microbial environment, different psychological traits. By the time they arrive, they might no longer be compatible with Earth's environment. They might not even be recognizable as human in the traditional sense. And if they've been traveling for 100,000 years, that's roughly 1/3 of the time modern humans have existed. That's enough time for significant evolutionary change. Sixth, catastrophe. Any single-point failure over a journey lasting millennia could doom the entire mission. A plague, a systems failure, social collapse, a meteor impact, civil war, religious conflict. Any of these could end the journey prematurely, leaving the ship drifting through space with no one left alive to reach the destination. Diseases could sweep through the population. In a confined environment with limited genetic diversity, a novel pathogen could be devastating. Earth's history is filled with plagues that killed significant fractions of populations. The Black Death killed perhaps 1/3 of Europe. A similar plague on a generation ship with nowhere to flee and limited medical resources could be extinction level. Social stability is not guaranteed. Over tens of thousands of years, conflicts will arise, factions will form, resource competition, ideological differences, generational conflicts. What if a generation decides they don't want to continue the mission? What if they want to turn around or stop somewhere else or just drift? The original mission planners are long dead. Their great-great-great-grandchildren's descendants might have different priorities. What mechanisms ensure compliance across hundreds of generations? Authoritarian control leads to resentment and rebellion. Democratic systems can lead to mission drift and changed objectives. There's no obvious solution. These aren't engineering problems with engineering solutions. These are fundamental challenges to the very concept of keeping humans alive across timescales, vastly exceeding anything our species has experienced. The longest continuous civilizations on Earth have persisted maybe 3,000 to 4,000 years, and even those have undergone massive transformations. Ancient Egypt persisted for about 3,000 years, but the Egypt of the Old Kingdom was very different from Ptolemaic Egypt. We're talking about journeys lasting 30 to 100 times longer. It's not just hard, it's arguably impossible to maintain human civilization across such timescales in such constrained environments. What about suspended animation? Cryogenic freezing? Put everyone to sleep and wake them up when you arrive. This is another staple of science fiction, but we have no evidence it's possible to freeze a human body and revive it without catastrophic cellular damage. The fundamental problem is that water expands when it freezes. Cells contain water. When that water freezes, it forms ice crystals that rupture cell membranes, destroying cellular structures. You can try to use cryoprotectants, chemicals that prevent ice crystal formation, but introducing enough cryoprotectant to protect all cells in a human body without toxicity is extremely difficult. Some small organisms can survive freezing because they're small enough that cryoprotectants can permeate their tissues. Some species of frogs can freeze solid and revive, but they're tiny compared to humans, and they've evolved specific biochemical adaptations for freeze tolerance. Humans haven't. We're not adapted for freezing. Our cells rupture, our tissues are damaged, our brains, with their delicate neural structures and trillions of synaptic connections encoding memories and personality, are particularly vulnerable. Even if we solve the technical challenges of freezing and revival, who maintains the spacecraft while everyone's asleep? You'd need automated systems reliable enough to function perfectly for thousands or millions of years without human intervention. We can't currently build electronics that last more than a few decades without maintenance. Satellites fail, electronics degrade, cosmic radiation damages circuits. You'd need systems that can self-repair, detect and fix problems, navigate hazards, all without human oversight, for geological timescales. And there's radiation. Space is filled with cosmic rays, high-energy particles that can damage DNA and electronic systems. Earth's magnetic field and atmosphere protect us from most of this radiation. In deep space, unshielded, the cumulative radiation dose over millennia would be lethal, even to frozen tissue. DNA damage accumulates. Even in a frozen state, high-energy particles passing through tissue cause ionization and molecular damage. Over thousands of years, the damage would be catastrophic. You'd need heavy shielding, which adds mass, which requires more fuel, which compounds the already impossible energy requirements, and even with shielding, some radiation gets through. Over geological timescales, the damage accumulates. What about sending robots instead of humans? AI systems that don't need life support, don't age, don't need food or water. This is more plausible, but it shifts the problem rather than solving it. Electronics degrade over time, especially in the harsh radiation environment of space. Cosmic rays can cause bit flips in computer memory, corrupting data. Electronics components fail. Circuits degrade. You'd need self-repairing systems that could maintain themselves across millennia. And you're not solving the speed problem or the energy problem or the expansion problem. You're just removing the biological constraints while the other barriers remain intact. And fundamentally, if we send robots to another galaxy, we haven't reached another galaxy. We've sent a probe. It's exploration by proxy, not human presence, not colonization, not the establishment of a second home for humanity. The robots might reach Andromeda, and they might send back data, but that data would take 2.5 million years to return. By the time we receive the first images from Andromeda, the civilization that launched the mission would be long extinct. The species that launched the mission might be extinct. The planet might be gone. The time problem is absolute. Biological organisms, human civilizations, and even technological systems don't persist across the timescales required for intergalactic travel. Time, combined with distance, creates a barrier as impenetrable as any law of physics. But what about the solutions offered by science fiction? Surely there are ways around these problems. What about warp drives, wormholes, or other exotic physics? Let's address those directly. Science fiction has given us warp drives, hyperspace, wormholes, instant teleportation, and a dozen other mechanisms for faster-than-light travel. These devices are narrative tools, plot conveniences that allow characters to traverse galactic distances in time frames compatible with human lifespans and story pacing. But do any of them represent actual solutions to the physical barriers we've discussed? Let's start with warp drives. The concept, popularized by Star Trek and other science fiction, involves warping space-time around a spacecraft to achieve effective faster-than-light travel without violating relativity. The idea is that the ship isn't moving through space at all. Space itself is contracting ahead of the ship and expanding behind it, carrying the ship along in a warp bubble. This concept has a legitimate theoretical basis in the Alcubierre metric proposed by physicist Miguel Alcubierre in 1994. The mathematics work, technically. You can write down equations describing a warp bubble that moves faster than light. The geometry of space-time can be arranged such that space contracts in front of a region and expands behind it, and anything in that region gets carried along. But there are insurmountable problems. First, the Alcubierre drive requires exotic matter with negative mass energy to create the warp bubble. Negative. Mass energy doesn't exist as far as we know. All matter and energy we've ever observed has positive mass energy. Negative mass energy would have bizarre properties, like gravitationally repelling rather than attracting. It might be impossible in principle, forbidden by deeper physical laws. We have no idea how to create it, no experimental evidence it exists, no theoretical framework that predicts its creation. Second, the energy requirements are astronomical. Early calculations by Alcubierre and others suggested you'd need more energy than exists in the observable universe. Literally. The negative energy density required was so extreme that you'd need to convert more mass than exists in all the galaxies we can see into negative energy. Later refinements by other physicists have brought this down somewhat. By optimizing the shape of the warp bubble, you might reduce the energy requirement to something like the mass energy of Jupiter. That's still 1.9 times 10 to the 27th kilograms, or about 1,000th of the Sun's mass. And that needs to be converted entirely to energy, then somehow manipulated into negative energy, which we don't know how to do. It's a slight improvement from infinite energy, but it's still completely impractical. Third, the warp bubble, once created, might be impossible to control from inside. To create the warp bubble, you need to manipulate space-time in front of and behind the ship. But to do that, you need to send signals or energy to those regions. And you can't send signals to the front of the bubble faster than light relative to you, because nothing can travel faster than light locally. So you'd need to set up the bubble before entering it. But then how do you accelerate, or steer, or stop? Some calculations suggest you'd need external infrastructure to set up and dismantle the bubble, meaning you can't use it to travel somewhere you haven't already been, which doesn't help for reaching new galaxies. Fourth, there are causality problems. Faster than light travel, even via warped space-time, potentially allows time travel into the past in certain reference frames. And time travel creates paradoxes and possibly violates fundamental physical laws. If you can travel faster than light in any meaningful sense, you can construct scenarios where you arrive before you leave, leading to grandfather paradoxes and violations of causality. The universe seems to prevent such violations, suggesting that something forbids true faster-than-light travel, even by clever manipulation of space-time. Fifth, recent papers suggest that even if you could create a warp bubble, crossing the event horizon into or out of it would subject you to infinite blue-shifted radiation. As you enter the bubble, from your perspective, the radiation from the rest of the universe would be blue-shifted to arbitrarily high energies. The cosmic microwave background, normally innocuous, would blue-shift into deadly gamma rays. You'd be incinerated instantly by the concentrated radiation. Similar problems occur when exiting the bubble. Warp drives, if they're possible at all, would require physics we don't understand, resources we can't obtain, and may be fundamentally forbidden by deeper principles. They're not engineering projects we haven't tackled yet. They're speculative possibilities that might violate laws of nature we haven't fully uncovered. What about wormholes? Theoretical shortcuts through space-time, connecting distant locations? Wormholes emerge naturally from the equations of general relativity. Einstein and Nathan Rosen explored them mathematically in 1935. They're called Einstein-Rosen bridges. On paper, they allow travel between distant points without crossing the intervening space. You enter one mouth of the wormhole, travel through a throat connecting two regions of space-time, and emerge from the other mouth, potentially light years away. But naturally occurring wormholes, if they exist at all, would be microscopic, far smaller than atoms, and would collapse instantly. They'd only exist for tiny fractions of a second before pinching off. To create a traversable wormhole large enough for a spacecraft, or even a human, you'd need exotic matter with negative mass energy to keep it open. Again, exotic matter with negative mass energy, which we can't produce and probably can't exist. The throat of the wormhole is unstable and wants to collapse. To hold it open, you need negative energy pushing outward, counteracting the positive energy trying to close it. And even if you could create a stable wormhole, you'd need to move one end of it to your destination. Which brings us back to the original problem. How do you get the wormhole mouth to another galaxy? You need to transport it there using conventional travel, which means you need to cross intergalactic space using normal propulsion, which we've already established is impossible. So wormholes don't solve the problem. You can't use a wormhole to go somewhere you haven't already been. You'd need to first travel to Andromeda the slow way, taking millions of years, then establish a wormhole connection. At which point the wormhole is useful for subsequent trips, but the first trip still requires conventional travel. Some theories suggest wormholes might exist naturally as remnants of the Big Bang, primordial wormholes created in the early universe's quantum fluctuations. But we have no evidence of this. We've never detected a wormhole. We have no way to find them if they do exist. And even if they do, no way to predict where they'd lead. A naturally occurring wormhole might connect our galaxy to a random point in the universe, possibly billions of light years away in the wrong direction. Or it might connect to a region of space-time in the early universe, or in a black hole, or somewhere completely inhospitable. And we'd have no way to stabilize them or control them. Wormholes don't solve the problem. At best, they shift it or require prior conventional travel to establish them. What about quantum tunneling or teleportation? Quantum mechanics allows particles to appear on the other side of barriers they shouldn't classically be able to cross. This is quantum tunneling. And quantum entanglement creates correlations between particles across arbitrary distances. Could these phenomena be exploited for travel? Quantum tunneling probability decreases exponentially with barrier width and particle mass. For a particle to tunnel through a barrier, the probability goes as e to the power of negative twice the barrier width times the square root of the mass times the barrier height. For macroscopic objects like humans or spacecraft crossing intergalactic distances, the probability isn't just low, it's effectively zero. You'd wait longer than the age of the universe, longer than the time until all stars burn out, longer than the time until protons decay, for a single atom to tunnel across intergalactic space, let alone an entire spacecraft. The numbers are so small, they're essentially indistinguishable from impossible. Quantum teleportation, meanwhile, doesn't transport matter. It transfers quantum states between entangled particles. To teleport a particle's quantum state, You need a pre-existing entangled pair of particles, one at the origin and one at the destination. You measure the state of the particle you want to teleport along with your half of the entangled pair, then send that classical information to the destination, where it's used to reconstruct the state on the other entangled particle. But crucially, you need to transmit classical information, and that information can only travel at the speed of light at best. So you haven't achieved faster than light communication or travel. You're still limited by light speed. And you need a pre-existing connection between origin and destination, requiring conventional travel to establish. These quantum phenomena don't provide shortcuts for macroscopic intergalactic travel. They're fascinating, they're real, but they don't help us reach other galaxies. What about uploading human consciousness into computers and transmitting the information as data? This is sometimes proposed as a way to achieve digital immortality and enable rapid space travel. You scan a brain, capture all its information, and transmit that information as a signal. Even if we could perfectly scan and upload a human brain, which we can't, transmitting that data across 2.5 million light years would still take 2.5 million years minimum. You're limited by the speed of light. Information cannot travel faster than light, period. Even if you compress the data maximally, even if you use the most efficient encoding possible, the transmission time is determined by distance divided by light speed. So you haven't solved the time problem. And there are profound philosophical questions about whether an upload is the same person or merely a copy. If you scan your brain and create a digital copy, did you reach another galaxy, or did a duplicate of you reach it while the original you stayed behind or was destroyed? Is personal identity preserved through such a process? These are deep questions in philosophy of mind that haven't been resolved. Cryogenic suspension we've covered. It doesn't solve the time problem or the distance problem. It potentially lets you skip subjective time, but the objective time remains, and the challenges of maintaining frozen tissue and systems for millions of years are enormous. Traveling at near light speed with time dilation reduces the subjective journey time, but doesn't solve the energy problem or the expansion problem or the practical challenges of surviving even a subjectively shortened journey. Every science fiction solution, examined carefully, either requires physics that doesn't exist, resources we can't access, energy scales that are impossible, or simply shifts the problem without solving it. The warp drives bypass the speed limit, but require exotic matter and impossible energy. Wormholes bypass distance, but need exotic matter and prior establishment of endpoints. Quantum mechanics doesn't scale to macroscopic objects. Digital transmission still faces light speed limits. None of these solutions are engineering challenges waiting to be overcome. They're speculative possibilities that likely violate deeper principles we don't yet fully understand, or that simply don't apply to the scale we need them to work at. And even if one of them somehow worked, they don't address the expansion of the universe. Most galaxies beyond the local group are receding faster than light due to cosmic expansion. No clever trick with space-time manipulation helps if the space between you and your destination is expanding faster than you can traverse it, even at light speed. The hard truth is this: science fiction isn't predicting our future, it's creating engaging narratives. The solutions it offers aren't roadmaps, they're plot devices designed to make stories work, and we shouldn't confuse the two. But there is one galaxy we will reach, or rather, one galaxy that will reach us. And the circumstances of that encounter reveal something profound about our place in the universe and our role in the cosmos. Throughout this entire discussion, we've focused on Andromeda as the nearest target, the most reachable galaxy, and the one that defines the boundary of possibility. If we can't reach Andromeda, we can't reach anything beyond it. But here's the ironic twist, the cosmic joke. We will reach Andromeda, or more accurately, Andromeda will reach us, because the Andromeda Galaxy and the Milky Way are on a collision course. Remember earlier when I mentioned that Andromeda is actually moving toward us at about 110 kilometers per second? This isn't random. This isn't coincidence. The Milky Way and Andromeda, along with about 80 other galaxies, form a gravitationally bound structure called the local group. Gravity, on these local scales, overcomes the expansion of space. The mutual gravitational attraction between these galaxies is strong enough to pull them together, and the two largest members, Andromeda and the Milky Way, dominate the dynamics. And in approximately 4 billion years, give or take a few hundred million, the Andromeda Galaxy and the Milky Way will collide. Not in the violent, destructive sense you might imagine from the word collision. Galaxies are mostly empty space. The distances between stars within a galaxy are enormous compared to the sizes of the stars themselves. When galaxies collide, individual stars rarely impact each other. The probability of any two stars colliding during a galactic merger is astronomically small. Instead, the galaxies will pass through each other like two clouds of dust interpenetrating. But their mutual gravity will distort their shapes dramatically. The spiral structures will be disrupted. Stars will be pulled out into long, tidal tails streaming off into space. The rotation of both galaxies will be disturbed. Gas clouds will collide, triggering bursts of new star formation. The supermassive black holes at the centers of both galaxies will eventually merge, releasing gravitational waves detectable across the universe. Over billions of years, over multiple passes, the two galaxies will merge, eventually forming a single giant elliptical galaxy. Simulations show this process in beautiful detail. First pass, the galaxies distort each other. Second pass, more disruption. Eventually, after perhaps 6 billion years total, a single merged galaxy remains. Our Sun, if it still exists, will likely be flung into a different orbit, perhaps ejected from the galactic center into the outer regions of the merged galaxy, or perhaps thrown closer to the center. The night sky will be unrecognizable. Andromeda's trillion stars will be mixed with the Milky Way's hundreds of billions. The merged galaxy, sometimes playfully called Milkomeda or Andromedae by astronomers, will dominate the local group. This is the ultimate irony. The galaxy we can never reach through our own efforts will come to us on its own, driven by forces we cannot control, on timescales we cannot influence. The only intergalactic travel humanity will ever experience is the involuntary kind, the cosmic collision we cannot prevent, cannot speed up, cannot slow down. We're passengers on a planet orbiting a star in a galaxy that's falling into another galaxy, and there's nothing we can do about it. And this collision illustrates a profound point. The universe operates on scales and timescales that dwarf human ambition. Galactic collisions take billions of years to complete. The forces involved are gravitational attractions between structures containing hundreds of billions of solar masses. The energies are unimaginable. And our entire civilization, all our technology, all our dreams, all our efforts are utterly irrelevant to the process. We're not actors in this cosmic drama, we're spectators, tiny temporary inhabitants of a small planet orbiting an average star in one of the two galaxies involved. We don't control this. We can't influence it. We can only observe and try to understand. The Andromeda collision also represents the end of our isolation in another sense. Currently, we live in a spiral galaxy with distinct spiral arms, active star formation, stellar nurseries where new stars are born, and a relatively dynamic structure. After the merger, assuming humanity or any descendants of humanity still exist, we'll live in an elliptical galaxy, a system with older stars on average, less active star formation, and a more uniform, less structured distribution of stellar populations. Elliptical galaxies are thought to be the end products of galaxy mergers. They're generally older, more sedate systems. The merger will also affect the expansion of the universe from our perspective. As the local group coalesces into a single gravitationally bound structure, that structure becomes increasingly isolated cosmologically. Everything beyond it continues to recede due to cosmic expansion. By the time the merger is complete, roughly 6 billion years from now, most galaxies beyond the local group will have receded significantly farther away. Some that are currently visible will have crossed beyond the cosmic horizon and disappeared from view. In the far future, trillions of years from now, the merged galaxy will be essentially alone in its observable universe. Everything else will have receded beyond the horizon. Future astronomers in that distant era will look out and see mostly empty space. The cosmic microwave background radiation, the relic of the Big Bang, will have redshifted beyond detectability. Individual galaxies will have redshifted beyond visibility. Those future scientists will face a universe that appears static, eternal, and isolated. They'll have no way to learn about cosmic expansion, the Big Bang, or the billions of galaxies that once populated the observable universe. Their cosmology will be fundamentally limited by the observational horizon created by cosmic expansion. We live in a unique era, a brief window in cosmic history, when the universe is both old enough to have formed complex structures like galaxies and planets and stars, and young enough that distant galaxies are still visible, still observable. In the deep future, that window closes. The universe becomes dark and empty from any local perspective. But even in our privileged position, with access to observations of billions of galaxies across billions of light years, we face the same fundamental limitation. We can observe, but we cannot reach. Andromeda will come to us not because we're special, not because we deserve it, not because we've earned it, but because gravity happens to have bound us together billions of years ago, long before humans existed, long before Earth existed, long before the Sun formed. It's cosmic coincidence, an accident of initial conditions set in motion by the distribution of matter in the early universe. It's not cosmic destiny. We're not chosen. We're not privileged. We're just lucky enough to be in a gravitationally bound structure with another major galaxy. And this brings us to the final, most sobering realization of all. What humanity's permanent cosmic isolation actually means for our species, for our future, for our understanding of our place in the universe. We're reaching the end of this journey through impossibility. We've examined the distance problem, the speed problem, the energy problem, the expansion of the universe, the cosmic horizon, the time and biology challenges, and the failure of speculative solutions. Every angle reveals the same truth. Humanity will never reach another galaxy. Let that sink in. Not probably won't. Not anytime soon. Never. Not in 1,000 years. Not in 1,000,000 years. Not in 1,000,000,000 years. Never. This isn't a technological challenge we might overcome with better engineering. It's not a question of developing better engines or discovering new physics. The barriers are fundamental, built into the structure of reality itself. The speed of light is an absolute limit, not a guideline. The expansion of space is accelerating, not slowing. The distances are too vast, measured in millions of light years. The timescales are too long, measured in millions or billions of years. The energy requirements are impossible, exceeding the total energy available to us. Humanity is not a galactic species. We're not even a full galactic species in our own galaxy. We're a species confined to one star system, with the possibility of maybe expanding to a few nearby star systems if we develop robust interstellar travel capability. which is itself extraordinarily difficult. But intergalactic space? Beyond our reach, forever. Most of the universe, most of the stars, most of the galaxies, most of the matter and energy that exists is permanently inaccessible to us. We can observe these distant realms through telescopes, we can study them, catalogue them, build theories about them, understand their physics, predict their evolution. But we cannot touch them, we cannot visit them, we cannot send even a single spacecraft to them, we cannot influence them in any way whatsoever. We are local, irrevocably, eternally local. Think about what this means. There could be civilizations in Andromeda right now, billions of intelligent beings living their lives on planets orbiting stars we can see through telescopes, building their cultures, creating their art, asking their own questions about the cosmos, wondering if they're alone. We will never meet them, they will never meet us, not because either of us lacks the will, not because either of us lacks the ambition, not because either of us lacks the curiosity, but because the universe itself forbids it. The laws of physics, the expansion of space, the cosmic horizon all conspire to keep us permanently separated. We are ships passing in the night on a cosmic scale, able to see each other's lights, but never able to signal, never able to meet, forever isolated by the vastness of space. The same applies to the Triangulum Galaxy, to the galaxies of the Virgo cluster, to the billions of galaxies scattered across the observable universe. Each one is an island, isolated and unreachable, potentially populated by life, by intelligence, by civilizations we'll never encounter. Each galaxy is a universe unto itself, from the perspective of any civilization within it. The universe is not made for exploration, it's made for observation. Think about exploration in human history. For thousands of years, humans explored Earth. We crossed oceans in primitive boats, taking enormous risks. We climbed mountains, reaching the highest peaks. We explored deserts, rainforests, polar ice caps. Every part of Earth, even the most remote, became accessible. Eventually, the deepest ocean trenches, the Antarctic interior, the Amazon rainforest, the Sahara Desert. Difficult, dangerous, but possible. We're a species that explores. It's part of who we are. Then we reached space, the moon. The first time humans set foot on another world, July 20th, 1969. It was difficult, expensive, required the resources of a superpower, but it was possible. The solar system. Mars, Jupiter, Saturn, all reachable in principle. Difficult, expensive, requiring advanced technology and long mission durations, but possible within the laws of physics and the lifespan of civilizations. We can conceivably send missions to every planet, every moon, every asteroid. We can explore the Kuiper Belt, the Oort cloud, the outer reaches of our solar system. But beyond that, a wall, an absolute unbreakable wall. It's as if the universe has drawn a boundary around our cosmic neighborhood with a sign that reads, "This far, no farther." And the tragedy, the cosmic tragedy, is that we can see past the boundary. Our telescopes reveal billions of galaxies, each containing billions or trillions of stars. We can study them in exquisite detail. We can measure their composition, their age, their motion, their distance. We can watch galaxies collide and merge over millions of years through simulations informed by observations. We can observe supermassive black holes at galactic centers. We can study the birth of stars in distant nebulae, the death of stars in supernovae, the formation of planets around other suns. But we're watching from behind an unbreakable window. We're prisoners with a view, able to see incredible wonders but never touch them, never experience them directly, never visit them. Some people find this depressing, And it is, in a sense. It means that the universe is stranger and lonelier than we hoped. It means that the dream of a galactic empire, of humanity spreading among the stars across multiple galaxies, of meeting alien civilizations in distant galaxies, is pure fantasy. It will never happen. Not because we lack ambition, but because the universe won't allow it. But there's another perspective. Maybe the lesson here is about scale and humility. We live on a planet 12,742 kilometers in diameter. A tiny blue dot, as Carl Sagan called it. Our galaxy is 100,000 light-years across, containing hundreds of billions of stars. The nearest major galaxy is 2.5 million light-years away, containing 1 trillion stars. The observable universe extends 46.5 billion light-years in all directions, containing about 2 trillion galaxies. We are tiny. Our planet is a speck of dust in a sunbeam, to use Sagan's imagery again. Our solar system is insignificant on galactic scales. Our galaxy is one among trillions, and yet we exist. We think. We wonder. We build telescopes and spacecraft. We develop mathematics and physics. We uncover the laws governing reality itself. We've gone from hunter-gatherers to a spacefaring civilization in about 10,000 years. We've decoded the human genome. We've detected gravitational waves. We've photographed black holes. We've measured the age of the universe to within a few million years. These are extraordinary achievements for a species that only gained self-awareness relatively recently in cosmic time. Maybe the point isn't to reach everywhere. Maybe the point is to understand everything. We cannot visit Andromeda, but we can comprehend it. We can understand the physics of stellar formation, galactic dynamics, spiral structure, dark matter halos, supermassive black holes. We can look at light from distant galaxies, analyze its spectrum, and decode their composition, their age, their motion, their history. We cannot touch the universe, but we can know it. And in some sense, knowledge is a form of reaching. When we understand a distant galaxy, when we can predict its motion and evolution, when we incorporate it into our models of cosmology and test those models against observations, we've connected with it in a meaningful way, not physically, not practically, but intellectually and scientifically. We've reached out with our minds across impossible distances and grasped something real about that distant place. Maybe that has to be enough, because here's the thing, it's the only option we have. The universe has made its rules clear. The speed of light is inviolable. Space is expanding and accelerating. Time is linear and irreversible. Energy is limited and conserved. Biology is fragile and short-lived. These aren't negotiable terms. They're fundamental laws woven into the fabric of reality. And within those constraints, humanity has achieved something extraordinary. We've gone from Bronze Age civilizations to spaceflight in a few thousand years. We've built machines that can see to the edge of the observable universe. We've decoded the human genome, understanding the molecular basis of heredity. We've split the atom and fused nuclei, harnessing nuclear forces. We've sent probes to the outer solar system, visited every planet, and landed rovers on Mars. We've built computers that process information at speeds unimaginable a century ago. We've developed theories that describe the behavior of matter from quantum scales to cosmic scales. These achievements are remarkable given our limitations. We're ephemeral creatures, living typically less than 100 years. We're confined to a fragile world vulnerable to asteroids, climate change, and our own mistakes. We exist in a vast cosmos largely indifferent to our existence, and yet we've managed to comprehend vast swaths of that cosmos through observation, mathematics, and reason. That's not nothing. That's actually incredible. But it's crucial to maintain perspective. We are not the center of the universe. We are not the purpose of existence. We are not destined to conquer the cosmos or spread across galaxies. We're one species, on one planet, in one star system, in one galaxy, during one brief moment in cosmic history. Most of the universe exists without us and will continue to exist long after we're gone. The sun will eventually expand into a red giant, possibly engulfing Earth, about 5 billion years from now. Long before that, in about 1 billion years, the sun's increasing luminosity will make Earth uninhabitable, and the vast majority of the universe will forever remain beyond our reach, whether we survive that long or not. This is the reality, not a pessimistic reality or an optimistic reality, just reality. The universe is as it is, regardless of what we wish it to be. Andromeda glimmers in the night sky, beautiful and untouchable, a fuzzy patch of light containing 1 trillion stars and perhaps trillions of planets. Behind it, billions more galaxies stretch across the cosmos, equally inaccessible, equally unknowable in direct terms. And in our own galaxy, trillions of stars wait, many with planets, some perhaps with life, maybe even intelligent life. We might encounter other civilizations within our own galaxy someday, though the distances and timescales make even that extraordinarily unlikely. But other galaxies? No, that door is closed, permanently. We live in the only part of the universe we'll ever inhabit. This is our home, the local group, a collection of about 80 galaxies bound together by gravity, spanning about 10 million light years, isolated from everything beyond by cosmic expansion. And maybe, in the end, that's the most important realization of all. Not that we can't go there, but that here, in this small corner of an incomprehensibly vast universe, we exist. We think. We wonder. We reach out with our minds toward the unreachable. And in that reaching, in that wondering, we find meaning not despite our limitations, but through them. The galaxies beyond will never feel our touch, but they've touched us with their light, with their existence, with the questions they provoke. For a brief moment in cosmic time, we looked up, saw them, understood them, and knew ourselves to be part of something vastly greater than ourselves. That knowledge, perhaps, is the only form of intergalactic travel we'll ever achieve. And perhaps, in a universe indifferent to our dreams, it has to be enough.